Yeah, so my talk is about side channel attacks on shared search indices. I'm an assistant professor here in computer science at Rutgers. I'll mention this is a collaborative work with a ragtag bunch of people. Liang is a PhD student at Wisconsin. Paul Grubbs is a PhD student at Cornell Tech. Jihua is an undergraduate from China who's doing an internship at Cornell. Vincent is a PhD student at UIUC, and Tom Ristapart is a professor at Cornell Tech. So we all collaborated on this last summer, and it's finally come to fruition. So this talk starts with the perspective that we'll think of a cloud service, a generic cloud service that holds user data. It could be Dropbox or GitHub or any of these other things. They're very different services, but they all hold user data, and they all provide an interface for users to navigate their own data in the form of a search API. You specify queries of some form, you get back your own documents, or maybe publicly accessible documents, hopefully with relevance scores or sorted according to relevance to help you find the best documents for what you're trying to do. And these services do this really quickly. So it's essentially instantaneous when you search. And the way they do this is by building an index that allows them to pre-compute queries, perhaps assemble different rows of this index and put it together. So this is going to come a few times in the talk, but this index is like just pre-computing terms that you might search for and then listing the records that contain that term. Usually other information is stored there. And of course, these services don't just provide a personal service for one user. They support attacks from services for many users. So typically, as many as they needed, possibly millions. And this talk today is about a different kind of attack on these services, namely a cross-user attack. So we're going to talk about, or I'm going to talk about, somebody who creates a valid account in one of these services and then tries to abuse this API to learn something about other people's private data. And so as far as the literature goes, I'm not aware of attacks of this form. So we're going to abuse something logical about how these APIs are designed. Specifically, this work gives attacks on 3 live systems. So we found a flaw in the industry standard architecture for supporting search on many user systems. And we were able to implement this attack against at least these 3 services, and it's probably effective against many more. Specifically, what we can do is in each of these services, we construct an oracle by abusing this API, and this oracle has this input-output behavior. It takes as input a term, so a word, and it outputs the number of documents in the service created by any user that contain that term. Okay, so what does this mean? So this isn't the sort of oracle that dumps entire plaintext documents. It's just giving you kind of query access into what other people have stored. What you can do with this, however, is in principle enumerate lots of medium entropy spaces by using this oracle and querying it many times, so brute forcing it. So in principle, you could enumerate which social security numbers have been stored in this service and which credit cards have been stored in the service. You can also do things like if you know 4 digits of the credit card, say the last 4 plus the bank that issued it, you could brute force the rest of the credit card number with this oracle in a few million queries. You can also do other sneaky things like estimating the popularity of certain technologies inside the service by looking at the counts that come out of the oracle. And so we, of course, only implemented this attack against data under our control. So we created victim accounts and then went after them. And we disclosed this to the services months ago. Zendoo is a service that provides, particularly security-conscious service, that provides unified personal cloud search. So you turn over your email password, your Facebook password, your Dropbox password to them, and they give you a search interface into all of that. So they were extremely security concerned and immediately cut off their API and slowed down the queries. They didn't completely prevent the attacks. Orchestrate.io went out of business for other reasons, conveniently for us. GitHub just acknowledged, yeah, they think this is a problem. They sent us T-shirts, and we've been working with them and they gave me this I hacked GitHub sticker that I'm very proud of. It's not clear they fully appreciate the situation, but we're working with them to advise them on what to do. And also in this work, at the end, I'll discuss countermeasures for how to eliminate this, because it's not a simple fix of just flipping a switch and it goes away. So there's good reasons why it's there. So search on a service like GitHub has to work with millions of users, billions of documents, and at a time it has to work over sensitive data that the users would prefer to keep private. And the way they support this at GitHub at least, and through many other services, this is through clouds, and it's not important to actually read that, but it's through third-party services that provide search as a service, or through these distributed enterprise search tools like Elasticsearch. So Elastic is this industry standard tool for enabling search on large amounts of data. Their clients include some of the largest, most important websites on the internet. This interface that they provide allows users to give expressive queries, usually typing in phrases or multiple terms that they want, returns results ranked according to relevance, and then, particular to what we're going to get into, enforces a very brutal, primitive form of access control. Okay, so here's how the service. Here's how these things are built, and so we have a service that's an Elastic instance that's holding many users' data. And so the first thing about how these things work is that this thing in the back end isn't aware of users. It just keeps track of documents, and it has no notion of access control internal to where the documents are stored. And where users' identities are implemented or kind of stored is in a front end that interacts with this back end search. And so the way the backend works is it indexes all of these documents together. Since it doesn't know who is who or whose document belongs to who, it just indexes them into one giant index. And then a user interacts with the front end. They have authenticated to it, or whatever. It's a secure connection. And the front end will receive a query and forward it to the back end. And the back end then responds with documents. And so if they're just my documents, those are the white ones. This backend, however, doesn't know what my documents are. It also sends back other people's documents. And so it's the front end's job now to just apply an access control filter. It allows us to redact those documents that we shouldn't see. It leaves those documents plus the scores in place, and I get my stuff back. So why would you build an index in this way? It's for several reasons. The first is that it's faster and saves space to build it this way. If you just pile everybody's stuff together, you can, you avoid spinning up many instances of this, like say a per user index, then you have to pay the overhead to index the same word over and over. It makes it faster. It also makes it simpler in the case of services where you share documents. It's very easy to turn, like if I share a document with somebody, they just turn the access control filter on for them. If I unshare it, they turn it off. This backend index doesn't have to be updated. So you separate out security from the indexing complexity. Another interesting reason this is done is because search works better when you have lots of documents. So this relevance thing, and I'll actually show you the formula for a relevance score later, these things get more accurate if you have a large corpus of documents. There's some sort of learning that goes on that figures out what are the more important terms. Okay. So and this will come up later in the talk, there's not actually one index that's sitting in this thing. In reality, there are in fact many indexes vertically partitioned, either on a per document, per user, or some other basis. And so there's some complexity in this backend of exactly where the document is stored, again, for performance and replication and robustness. Okay, so that's the setting. This is the way these systems look. Now let's think of what an attacker would do to abuse this. And the root of the problem is going to be this mixing of users in the backend. So a user is going to be just, an account an attacker is just going to be a valid account that we create. So this account only interacts through this interface. It doesn't have access to the backend directly. And it can do everything a user could do. So it can create documents, it can edit them, and they'll get thrown into the index. And it can also issue queries and get relevance scores. And we're going to assume that access control is properly implemented. So it only ever receives its own documents back. The key observation here, like the linchpin where everything starts, is that the scores that we see on our own documents are mathematically functions of other people's documents. That's where things start to go wrong, because you now have some output that has some private, you get an output like 9.61 that's actually computed over this entire corpus. Maybe one of these, they're usually called shards or partitions in the back end, and it's computed over all that. It depends on everything that's in that shard potentially. So it's a matter of establishing if this score that we see, which depends on all of these documents, really corresponds to an exploitable side channel or not. Okay. So to see why that's a problem and why we eventually get this oracle that I described at the start of the talk, let me show you how, sketch how these scores are computed. So most services use something called TFIDF, or one of its infinite number of variants, or there's stuff like BM25, which are morally similar enough for the attacks to work. They kind of, for TF-IDF at least, we have this form of, we can score a particular single term query against the document as the product of the term frequency and the inverse document frequency, the IDF. The term frequency is the number of appearances of that term in the document, so cat appears 5 times, so that's 5. IDF is a more complicated formula that is meant to go down, so this IDF should go down for the word cat as cat becomes more common in the corpus. And so the IDF is there to make multi-term queries work better. As you know, if I search for cat dog, if cat appears everywhere, we should pay less attention to that. We should look for dog as the more weighty term, and IDF will ensure that that happens. Right, so that's just what I just said. And so here's the root problem, is that the score that we output here depends on this IDF, and the IDF is the number of documents that contain the particular term. And so, so that's our view into what could go wrong. And so this observation that something could go wrong is not new to us. Well, we came up with it independently. The story is that I've been interested, so I work in cryptography mostly, and I've been interested in encrypted search. And so I was learning about how plain text search works, and I realized the plain text stuff wasn't even properly designed. But so when we looked into this, we realized this might be a problem. Let's think about it. We dug into the literature. There's a paper at FAST in 2005 that made this observation. And the substance of their observation was basically, I could solve this equation if I knew all the variables except for this. I could get this one right here. And so they observed that maybe in Apple Spotlight, so desktop search, that 2 desktop users could exploit this side channel, but they couldn't implement it, or they did not implement it, and they cited some difficulties for why. And so let me review why this is not just a trivially exploitable problem in practice. So in fact, the story was we told some of these practitioners about this problem, and they were surprised that the practical factors didn't get in the way. So the first factor that complicates this side channel is the one cited by Butcher and Clark in 2005, which is that in practice, if you're going to attack a service, you don't know what scoring function they're using. And that's because TF-IDF variants often have many hidden variables that are hand-tuned for the specific setting. So GitHub wants code search to work, so they kind of munge around TF-IDF to make it work better in their setting. Next, very interestingly, is the churn in the services creates lots of noise in the scores you're getting back. So this is a plot of we just created a document and with a particular term and searched for it over and over in GitHub. And over the course of 1 minute, we noticed that this looks like the effect of hitting 2 different inconsistent replicas of the same shard with their load balancer that are giving us different scores as they go back and forth. So we're not even getting a consistent score. And this is over the course of an hour, watching the score drift. So this happens from, like I said, inconsistent replicas, also from other users writing stuff into that index in between your queries. So another, this is probably the most difficult thing that confounds an attack, is the partitioning in the back end will be really confusing if you're not careful. So from an attacker's point of view, you're interacting with a front end that's speaking with many different possible backends. When you issue a query for a word, that's forwarded to, assuming it's a query over the entire corpus, so the public code on GitHub, for instance, it will be forwarded to all of the shards, some of which respond with results, and then are aggregated in this front end. And the complicating factor here is that, say, this 8.12 was computed by a shard that has different data from this shard that computed the 9.61. And moreover, this partitioning is completely opaque to the user, and that you can't tell that this came out of one shard and this came out of another shard. And if I wanted to draw an inference from those numbers, I would need to know which came from which shard. And I guess I'll make this a little more clear later, but the side channel will only work, within this shard. So these shards are completely independent, other than, from being part of the same cluster. The scores they're computing are on independent data. So the next complicating factor is rate limiting. So these attacks want to issue lots of queries. Of course, the services will limit you just for their own reasons, not for security, but because they don't want people to overwhelm the service. Next is sort of related to that is node deleting. So in general, if you want to probe the system and learn something about the documents in there, the attacks are going to involve writing in stuff and then watching what happens. So you sort of perturb the system and see what happens. And because of the way these things are designed, deletions are very low priority in their design and often take up to 24 hours to happen. So if you, as an attacker, write something in there, you have to be very careful not to detect your own instance. So if you're trying to determine, has this person's social security number been stored in the service, and then you write that social security number into the service, you have to be careful to not get fooled by your own writing when you do it. Okay, so that's the overview. So I have a good 10 more minutes. So I'm going to discuss the principles for how we implemented this and in 2 stages. So first I'm going to describe the basic simple attack that we call score dipping. And here, let's make an assumption that there's a single shard service. So we'll ignore the sharding complications. And we'll just say we want to, and we'll assume we can write files into the service. And our goal now is a very simple goal. We just want to know, you give me a term, like a credit card number, whatever. I want to answer the question, did somebody else write that credit card number into a document somewhere into that shard? And so our attacker doesn't know the score function. All of those other complications are coming into play. So here's what the attacker is going to do. The attacker is going to first establish a baseline score in a this step is independent of the victim term that we're after. And this attacker step will pick a long random term, think like 30 bytes, whatever, and then write that into a document and put it into the service. So now it's stored there. We know it's there. We just query for that term to get back our own document, along with the score, which is the part we're interested in. It's 9.02 or something like that. Who knows what it is? And we remember that score for the second phase. So we've queried that. And now we're going to probe for the victim term W in the second part. So here, we go to our document that we previously created, and we overwrite that long term to now contain the term W. And then we search for W. So access control will prevent us from seeing this document. We're not going to get that one back. We get back our own document, maybe other stuff, and then the question's easy to answer. We generally expect to only get back our document, but it might have a different score. Let's call that score S prime. Okay, and that's what we're going to do. We're going to compare the score on of S prime to S. And so there are 2 cases here. If the victim term is not written anywhere in the service, nobody else has stored that credit card number, then these scores should be the same. Because in both cases, the document frequency, or the inverse document frequency, should be the same because the term appears exactly once in the service, right? Either R appears exactly once and W will appear exactly once because I wrote it in there. In the case where somebody else had already written W, then the original baseline score will be higher. So the IDF will drag down the second score because W is now a more common term. It appears in 2 documents instead of 1. Okay, and even if this difference was relatively small, we could amplify it by writing in a bunch of documents here. Actually, there's some details there that I don't want to get into, but that's the basic concept. The bottleneck, if you want to implement this, it's fairly fast, but if you're an attacker who wants to brute force a big space, the bottleneck is going to be generally writing in to the service and then waiting for the index to be updated so that the second stage will successfully return the document you just created. And in all the services we probed, it was about a minute where you had to wait for this to happen. So a minute doesn't scale very well. This, however, is not much of a limitation because you can often parallelize this and just create a bunch of free accounts and do them each in a minute, and so you're going to get fine throughput. Okay, so that's the basic assumption on a single shard. Just tell me, did somebody else store this document? In a multi-shard setting, things are much messier. And so let's think about why. So let's think of the same setting where we're after a victim term W that's in one of these shards. And we want to know, was W stored somewhere in this backend? And the attacker, to start, doesn't know how many shards there are, doesn't know the load balancing policy, and so on. So if you just try and carry out the attack, what happens is you'll create your probe, the score dipping attack. You'll just create your random document, and it'll get placed somewhere and under a method not under your control. And when you do that, anything you do with this document will be independent of the existence of this document. So your attack won't work. So a natural thing to try and do is to just repeat the attack over and over until you get here, and then you'll get what you want. But that doesn't work because when you do this, let's say we do that. So we carry out the attack against this one shard here. So we go back and we write the victim term into that shard, and it gets written there. And then we do the second stage, and we learn, OK, it wasn't written there. When we come back and we do this again, we create another document, maybe with another random term. If we go back to the same shard, and again, we don't a priori have a way to prevent that, then we'll just detect our old document there. Like, we can't distinguish from the input-output behavior here which of these two cases we're in. If we revisited an old shard where we wrote WN, and recall we can't delete it unless we're willing to wait 24 hours, or we visited a new shard that happened to contain the victim term that somebody else wrote in. And so what will happen is that in the later stage, we'll detect our own documents, and that's a problem. So we found a way that an attacker could get around this problem. And it involves a pre-computation phase. Instead, before we go directly to this, we're going to try and reverse engineer this back end through the front end to figure out what's going on back here through this interface. And what we're going to do is something we call shard mapping, where we want to, over time, just using this interface, place exactly one document on each shard, so that we know which documents are on, we have a set. Say if they're in shards, we'll come up with a set of in documents that we know are placed on different shards, and then we'll use that as a second, faster phase for carrying out the attack. And so here's what shard mapping looks like. The basic idea is to create documents, let them get assigned to shards, however the system likes, and then kind of do it over and over. And then the important part is that when we place the second document, we're going to try and figure out, was this placed on a shard we've already seen before? Was this placed on a shard along with a document that we created previously? And the way we're going to do this is we're going to use that side channel from before as score dipping, but against our own document. So we're going to establish a covert channel between these documents that works when they're on the same shard. So we're going to write terms in and watch for score fluctuations. And if we see score fluctuations, then we'll know they're on the same shard. But if they're not on the same shard, then we won't see those fluctuations. We know we've gotten to a new shard with our document. And so over time, we'll do this and we'll get repeats. But the nice thing is when we get a repeat, we could just forget about that document. I'll think of it as deleting it, but we're just not using it. We can't delete in the system. We're only writing random junk into their system right now, so the delete problem isn't complicating our lives. So over time, we do this, we get repetitions, we eventually place a document on every shard. And we're never totally sure that we got every shard. We get a probabilistic guarantee. You could just run it for a while, and eventually you'll stop seeing new shards. If you wanted to try and estimate how long you should run this, it's like a coupon collector problem, where you're collecting shards over time. If they're in shards, you expect n log n attempts before you've seen them all, something like that. In the paper, we put some effort into showing you can speed this up, you can avoid delays through the APIs and so on. But this is the high-level technique. So the second stage of the attack is exactly like before. I want to know, did somebody write a victim term W somewhere into this index? And then I just run it with this document, with this document, with this document, with this document. And I can test every shard independently. So I can actually do more than just tell you if somebody else stored the victim term. I can tell you which shards they stored it on. So that is, in effect, more information about, say, what's going on inside of this shard. If I could figure out if a particular customer was on that shard, now I could focus on their information. So that's the main way the attack works. As a case study, just to put some numbers on this in GitHub, the constraint for the API was 5,000 queries per account per hour. The index takes a minute to update. The shard mapping phase took a few days. We found they had 191 shards at the time we ran the attack. I think they spin one up occasionally. We did. I don't remember if we ran it again. Anyway, the effect is with one account, you can test in about a minute if a term was stored on any one of those shards that we saw. Again, the only bottleneck is writing. And you can do that with multiple accounts in parallel. To put some math on this where it might affect the user, if you had, you knew which bank issued a credit card number, you had the last 4 digits, you could brute force the rest of a credit card number in about 200 hours with one account, which is fully parallelizable. I'll note now that the other services were similar, perhaps easier to attack. They had fewer shards, so shard mapping ran faster. The attack, and this is an appendix in our paper, will still work even if you don't get those relevant scores explicitly. So there's an extension of the attack that still works by just looking at the ordering of documents that it gets. So the ordering of the attacker's documents, by just looking, did I get A then B or B then A? That's enough to make it work. It slows down the attack. Which actually leads, this should have been on the next slide actually, to how do we fix this problem? And so there are lots of countermeasures you could think of, kind of easy ones. There's no perfect solution that we've been able to design yet. So one very simple to suggest thing to eliminate this side channel are per user indices. You just assign each user to their own index, and then you don't have the logical side channel anymore. Of course, you pay, there are reasons why we didn't do this to start out with, right? You pay a per user overhead to spin up these indices. It complicates things like sharing, and also diminishes the quality of the search you're getting, because some of these indices may be very tiny if user doesn't have much data. A more interesting countermeasure that we suggest is to try and train the document frequencies, that's the side channel, on auxiliary public data. So when you're computing your TF-IDF, instead of inputting the actual corpus here, draw out this corpus from a model that you've trained on some other corpus. And of course, this has its issues. You're not going to get as good search quality. I mean, you might get better. I mean, it's undetermined what kind of search quality you get from this. And of course, you have to modify these enterprise systems to do this very different type of operation. Another one is to think of annotating. So give some notion of private versus public to that backend, which currently does not have one. And what I mean is, when you're inputting these in, modify the indexing software to know which documents are public and therefore okay to leak information about, and which ones are private and should be protected. And so when you do this, now you can modify the way you compute those document frequencies. You can, when you're computing the IDF, you only compute the IDF. You just pretend it's only the public white documents that are viewed. So you don't increment the document frequency for the private ones. Of course, this comes with its own implementation problems, probably easier than the first one. And again, we don't know what kind of search quality you'll get. So if your search depends on a lot of terms that are only in private documents, then you won't get good results from this. One thing that I think everybody suggests to me, especially cryptographers who are predisposed to this idea, is let's just add some noise to the scores and try and kill the side channel that way. And I think that's not likely to work, because the side channel is actually quite strong, and you could just correct for the errors that noise would introduce. Okay, I think my timer's saying I should stop soon, but okay, well that's good, because this is my last slide, and then that's all I had. So thank you.
So would noise help make it persistent for noise, right?
I don't think noise is a good approach. I just put it on the slide because I end up having to explain or rethink of why I don't think it's a good idea every time. It's because it works even if you don't show me the scores. Just looking I can actually do a more advanced attack that only needs the order of documents. You'd have to add enough noise so that the order of documents starts getting reversed. And then, I mean, you're screwing with the scoring, like the quality, the relevant scoring itself, like the whole purpose of the scoring. And I would only consider that direction if these other approaches were just totally impractical.
So you don't think you could use noise to do something sort of midway between, doing it as computing it on all the documents and then having public and private and only using the public? Like you could sort of use all the public and then use the private in a differentially private way.
So, yeah, I think like the problem is if you wanted to like take differentially private thinking here, the individuals, I guess, would be documents or user accounts or something. And so you want to hide the presence of just a single document that contains that number. Or you might be able to do that, but what if I write that social security number in 1,000 documents or something? Then you're not hiding that fact, which, yeah, it just doesn't seem to match up, like noise versus what we're trying to protect here. Yeah.
I'm just curious, what type of sensitive information gets stored on GitHub?
Credit card numbers.
They just store credit card numbers?
People, you use it. It's just I sort of treat GitHub as a generic, like, personal storage for my work files. And so yeah, the story for, like, maybe it would have been good to have a slide on this, is GitHub released the search. They opened up their search API some number of years ago, and then immediately shut it down for a few days because they found that people were storing sensitive information in public repos all over the place, and that there just wasn't a live search service to help you find it. In particular, they were storing RSA private keys in scripts that were everywhere. But there's also this other, like, personal information, I think, that was found also. So yeah, it's the Zendoo use case is maybe more compelling from, like, people are really, I mean, Zendoo's one of their goals is security, and so that you can turn over access to all of your data to them. But I'd like to stress it's actually an industry standard approach. If you go to these different search tools, they recommend shared indices, use them this way. And so even if it's not just GitHub, there are likely other services online that should move away from this architecture, or at least put in place countermeasures.
All right, thank you.